last chapter on inventory models. So the content of today's lecture is, first we're going to discuss the basic economic order quantity model, which become the basis for everything that we're going to discuss the rest of today's lecture. And then we're going to discuss about economic production lot size models. And then we're going to add more complexity in the model, such as the planned shortages. And then we'll consider the EOQ model with quantity discount. And the first four is based on the deterministic models. And then starting from 10.5, we'll go into the probabilistic demand, in which the demand will be depend on some probability. So we'll cover topics such as single period inventory models and the order quantity and 3 order point model with probabilistic demand, and finally the periodic review model with probabilistic demand. So let's go straight into setting up the background for our inventory discussions. So basically everyone knows what is inventory. By definition, inventory refers to either goods or materials which is held by an organization for use sometime in the future. So the items carried in inventory can include raw materials, purchased parts, components, sub-assemblies, work in progress, and most of the time we'll think inventory as a finished good and supplies. So basically there are two primary reasons why organizations need to stock their inventory. Number one is to take the advantage of the economies of scale that exists due to the fixed cost of ordering items. For example, if you need 20 items every day, then instead of buying it 20 every day, then you can just buy 100 that could last for 5 days, and therefore you could save on the shipping cost. And the second reason is to buffer against uncertainty in customer demand or disruptions in short supplies, especially when it comes to festive seasons where the demand will peak. Even though inventories serve an important and essential role, the expense associated with financing and maintaining inventories is a substantial part of the cost of doing business. In some large organizations, the cost associated with inventory can run into millions of dollars. So in the applications involving inventory, managers must answer two important questions. The first one is, how much should be ordered when the inventory is replenished? Number two is, when should the inventory be replenished? So virtually every business use some sort of inventory management model or system to address the preceding questions. For example, the Hewlett-Packard works with its retailers to help determine the retailers' inventory replenishment strategies for the printers and other HP products. So the purpose of this chapter is to show how the quantity models can assist in making the decisions on how much to order and when to order. So we will first consider the deterministic inventory models, for which we assume that the rate of the demand for the item is constant, or at least nearly constant. And later, in the later part of the lecture, we'll consider the probabilistic inventory models, for which the demand for the item fluctuates, and it can be described only in probabilistic terms. Let's go to the first one, the economic order quantity model, or in short, we just call this EOQ. So the EOQ model is applicable when the demand for the item is constant or nearly constant, and when the entire quantity orders arrive in inventory at one point of time. For example, if you order 1,000, all the 1,000 arrive at one point of time. The constant demand rate assumption means that the same number of units is taken from the inventory each period of time. It can be 5 units every day, 25 units every week, or 100 units every 4 weeks, and so on. So to illustrate the EOQ model, let us consider the situation faced by this one company, R&B Beverage. So R&B Beverage is a distributor of beer and wine and some soft drink products. From the main warehouse, the RNB supplies nearly 1,000 retail stores with beverage products. So the beer inventory, which constitute about 40% of the company's total inventory, average approximately 50,000 cases. With an average cost per case approximately at $8, so RNB estimates the value of its inventory to be $400,000. So the warehouse manager decided to conduct a detailed study of the inventory costs associated with Bud Beer, which is the #1 selling RNB beer. The purpose of the study is to establish how much to order and when to order for Bud Beer that will result in the lowest possible total cost. So as the first step in the study, the warehouse manager obtained the following demand data for the past 10 weeks. You can see during the first week, the demand is 2,000. It increased 25 units in the second week, and it decreased to 1,950 in the third week, and so on. So the total cases is 20,000, which is we could say that the average cases per week is 2,000 cases. So strictly speaking, these weekly demand figures do not show a constant demand rate. It fluctuates a little bit. However, given the relatively low variability exhibited by the weekly demand, as you can see, in the first week is 2,000 and it increased by 25, it decreased by 50 and all that. So we could say that the variation is quite low. So the inventory planning with a constant demand rate of 2,000 cases per week appears as acceptable, and we can assume that this is relatively constant. So in practice, in real life, you'll find that the actual inventory situation very seldomly, if ever, satisfy the assumptions of the model exactly. Therefore, in any particular applications, the manager must determine whether the model assumptions are close enough to reality for the model to be useful. And in this situation, because demand varies from the minimum is 1,900 in week 9 to the highest is in week 5, which is 2,100 cases, the assumptions of constant demand of 2,000 cases per week appears to be reasonable approximation. So the decision involving to answer the questions of how much to order, okay, it involves selecting an order quantity that draws a compromise between #1 is we want to keep small inventories and ordering frequently, and #2 we want to keep large inventories and ordering infrequently. So the first alternative can result in undesirably higher ordering cost because you need to order many times and you need to order frequently, so the shipping cost will be higher. And the second alternative can result in undesirably high inventory holding cost because if let's say you buy like 10,000 stock at one time, you can minimize the shipping cost, but then you're going to have to pay for the storage cost. So therefore, to find an optimal compromise between this conflicting alternative, let us consider a mathematical model that shows the total cost as the sum of both of these costs, which is the holding cost and the ordering cost. So what is a holding cost? Holding cost is the cost associated with maintaining or carrying a given level of inventory. And this cost depends on the size of the inventory. So the first holding cost to consider is the cost of financing the inventory investment. For example, when the firm borrows money, it incurs an interest charge. If the firm uses its own money, it experiences an opportunity cost associated with not being able to use the money for other investment. In either case, an interest cost exists for the capital tied up in inventory. So this cost of capital is usually expressed as a percentage of the amount invested. So the RNB estimate the cost of its capital is at the annual rate of 18%. So a number of other holding costs such as insurance, tax, breakage, pilferage, and warehouse overhead also depends on the value of the inventory. The larger it is, the larger the insurance will be, the larger the taxes will be, and etc. So the RMB estimates these are the costs at an annual rate of approximately 7% of the value of its inventory. And therefore, the total holding cost for the RMB beer inventory is 18 plus 7%, which is 25% of the value of the inventory. The cost of one case of pub beer is $8. When we compute the annual holding cost rate of 25%, the cost of holding one case of pub beer in inventory for 1 year is equal to 0.25 times $8, which is $2. So the next step in inventory analysis is to determine the ordering cost. This cost, which is considered fixed regardless of the order quantity, covers the preparations of the voucher and the processing of the order, which is including the payment, postage, telephone, transportations, invoice verifications, receiving, and so on. For RMB beverage, the largest portions of the ordering cost involve the salary of the purchasers. An analysis of the purchasing process shows that a purchaser spends approximately 45 minutes preparing and processing an order for pub beer, with a wage rate and fringe benefit costs for purchases of $20 per hour. The labor portions of the ordering cost is $15. Making allowances for paper, postage, telephone, transportations, and receiving cost at $17 per order, the manager estimates that the ordering cost is $32 per order. That is, RMB is paying $32 per order regardless of the quantity requested in the order, whether it's 500 or 10,000 or etc. So the holding cost, the ordering cost, and the demand informations are the three data items that must be known prior to the use of the EOQ model. After developing this data for the RMB problem, we can look at how they are used to develop a total cost model. We begin by defining Q as the order quantity, and therefore the how much to order decision involve finding the value of Q that will minimize the sum of holding and ordering cost. The inventory for pub beer will have a maximum value of Q unit, which is around here, when an order of size Q is received from the supplier. RMB will then satisfy the customer demand from inventory slowly until the time T, until the inventory is depleted, at which time another shipment of Q units will be received. So it's going to be on the graph, like on the right hand side, start with Q, and then with time, at time T, it will replenish, and then we'll have another order. It goes back to Q, and then it goes down again. And as you can see, the height of the Q here is relatively constant. And remember that this is the very first assumptions that you need to satisfy in order for you to use the EOQ model. So we assume a constant demand, and the graph of the inventory is shown as a zigzag like this, And the average inventory is shown by the dashed line over here, which is half of the Q, or Q divided by 2. And this level should appear reasonable because the maximum inventory is Q and the minimum is 0, and the inventory declines at a constant rate over the period. So the holding cost can be calculated using the average inventory. That is, we can calculate the holding cost by multiplying the average inventory by the cost of carrying 1 unit in inventory for the stated period. So the period selected for the model is up to you. Like you can have like 1 week or 1 month, 1 year, and so on. However, because the holding cost for many industries and businesses is expressed as an annual percentages, so most inventory models are developed on an annual cost basis. So here we have I, which is the annual holding cost rate, and then we have C, which is the unit cost of the inventory item, and CH is the annual cost of holding in 1 unit in inventory, and therefore CH is equal to I multiplied with C. So the general equations for the annual holding cost for the average inventory of, remember, we are computing this on Q divided by 2, or half of Q, okay, as we discussed from the previous slide. So the annual holding cost is equal to the average inventory, okay, which is 1 over 2Q, multiplied with the annual holding cost per unit, which is CH. So the annual holding cost is 1 over 2Q times CH. So this is one part of the total cost model. Now the other part involving the annual ordering cost. So the goal is to express the annual ordering cost in terms of the order quantity Q. So the first question is, how many orders will be placed during the year? Let's D denote the annual demand for the product. Okay, so we assume that every year there are no, we don't assume. Every year there are 52 weeks. Yeah. So D equals to 52 weeks multiplied with 2,000 of cases, divide by which is 2,000 cases per week, which is equal to 104 cases per year. So the demand for the whole year is 104,000. Okay, so we know that by ordering Q units every time we order, we'll have to place D divided by Q orders per year, which is the demand divided by the number of the inventory order per year. So if the cost of placing one order is CO, the cost of one shipment is equal to CO. So the general equations for the annual ordering cost is given below. So the annual ordering cost is given by how many times you order per year multiply with the CO. So how many orders is D, which is the annual demand, divided by the quantity. Okay, quantity of inventory at one point of time, multiply with CO. And therefore we have already completed our total cost, which is the TC, the total cost, is the annual holding cost, which is 1 over 2 QCH, plus the annual ordering cost, which is D over QCO. And this whole thing is what we call as the total cost. Now we can compute the total annual cost, TC, and TC depends on the annual holding cost and the annual ordering cost. So the TC is given by, we know CH is equal to $2, and previously we have shown the calculations for the CO, which is equal to $32. With the demand, the annual demand is 104,000 a year. So we include all this into these equations, and we get TC is equal to 1 over 2Q times 2 plus 104,000 divided by Q times 32. And here we have Q plus 3.3 millions divided by Q. Now we want to solve for this value of Q that will minimize the total cost. And to do this, we'll just choose several numbers. Like for example, maybe we can have the order quantity of 5,000, 4,000, and 1,000. And for each of these, we'll compute what will be the holding cost, what will be the ordering cost, and what will be the total cost. So with the order quantity of 5,000, we can see that the total cost is 5,600. And as we decrease the order quantity, you can see that the total cost also decrease. But if we further decrease to 1,000, we can see that the total cost is now increased. Yeah. So we say that the total cost lies somewhere between 1,000 to 2,000, because from 2,000 is 3.6 thousand, and it goes up again at 4.3 thousand, and then we have to choose a number which is between these two figures. But to do this accurately, what we can do is we can solve for this equation. So Q, by doing the algebraic manipulations, we can put this Q on the left hand side, and we can have the rest of them to be on the right hand side. So if you look at the equation for the total cost, this is given by 1/2 Q of CH plus D divided by Q times CO. So you take all the Q and put it on the left hand side, and then we have Q squared on the right hand side, and what we have on the right hand side is everything else, which is the 2 times D times CO divided by CH. And to get the Q, we need to square root them, and then what we have is just plug in all these informations. The Q optimal, or the Q, or the quantity that would minimize the total cost, is 1824. And as you can see from this graph, you can see that as the order quantity increases, the annual ordering cost will decrease. Because, for example, if the demand is 104, okay, and you just place the order once every year, so of course you just need to pay for one ordering cost, but then your annual inventory cost will be high. Okay, so as the ordered quantity increases, the annual inventory cost will go up, but the annual ordering cost will go down. So what we want to look for is somewhere around here, which minimizes both the annual inventory cost and also the annual ordering cost. And the minimized number here is at 1824, which is the annual, if you put this 1824 into the equations, you get the total annual cost for the bulk beer, which is 3649, which is the minimized total cost. Alright, I try to go to the next slide. It doesn't work. Now we have already answered the questions on how much to order, and the answer is 1,824 cases. So we go to the next question, which is when to order. So to answer these questions, we need to introduce the concept of inventory position. What is inventory position? The inventory position is defined as the amount of inventory on hand plus the amount of inventory on order. So the decision, when you want to make these decisions on when to order, it is expressed in terms of the reorder point. Like, you know, the reorder point is when your inventory replenish up to a certain point in which you think that, okay, you need to reorder it now, at this moment. So that is called the reorder point. So the manufacturer of bulk beer guarantees a 2 days delivery on any order placed by RMB. And therefore, we can assume that RMB operates, let's say, we assume RMB operates at 250 days per year after removing all the festive season and probably the weekends. And therefore, the annual demands of 104,000 cases, it would imply a daily demand of 104,000 divided by 250, which is around 416 cases a day. And therefore, because the supplier guarantee a 2-day delivery, we can expect these 2 days multiplied with 416 cases per day, which is equal to 832 cases of bulk to be sold during these 2 days that it takes a new order to reach RMB warehouse. So in inventory terminology, the 2-day delivery period is referred to as the lead time for the new order. And the 832 cases demand anticipated during this period is referred to as the lead time demand. And therefore, RMB should order a new shipment for bulk beer from the manufacturer once the inventory reach 832 cases. And while, you know, it takes 2 days for this stock to replenish, and by that time we'll receive a new order at once. So for inventory system using the constant demand rate assumption and a fixed lead time, the reorder point is the same as the lead time demand. And for these systems, the general expressions for the reorder points is given by R, where R is the reorder point, and it is given by D times M, where D is the demand per day and M is the lead time for the new orders. So therefore now we can answer the questions on how frequently the order will be placed. The period between orders is referred to as the cycle time. So we already defined D divided by Q as the number of orders that will be placed in a year. Okay, based on the demand. Demand is 104,000 divided by the Q. Q optimal is given by 1,824. So if we take D divided by Q, we get 57. So 57 is the number of orders the RMB will place for bulk beer each year. So every year, throughout the annual calendar, there are 57 number of orders. So if RMB place 57 orders over these 250 working days, so it will take approximately 250 divided by 57, which is 4.39 working days. And therefore, we can say that the cycle time in this case is given by 4.39 working days. And the general expressions for the cycle time of the T is given by this. Okay, the cycle time is given by 250, which is the working days of in 1 year, divided by D divided by Q optimal. Okay, and then you have 4.39. Even though substantial time may have been spent in arriving at the cost per order, which is $32, and the holding cost rate, which is 25%, we should realize that these figures are at best good estimates. Remember, this is a deterministic model, which means that we really assume that this is the right figure. Therefore, we might want to consider how much the recommended order quantity would change with different estimates, ordering and holding cost. So, and this falls under the sensitivity analysis. To determine the effects of various cost scenarios, we can calculate the recommended order quantity under several different cost conditions. So the table below shows the minimum total cost order quantity for several cost possibility. We just consider like 4 circumstances here, in which there are 2 possible inventory holding costs, 24 and 26, and 2 possible cost per order, which is 30 and 34. Of course, we can simulate much more if we really want to do this, but let's talk about the sensitivity analysis. As you can see from this table, the value of the Q optimal appears relatively stable, even with some variations in the cost estimates. And based on these results, the best order quantity for bulk beer would be in the range of 1,700 to 2,000 cases. And if operated properly, the total cost for the bulk beer inventories should be close to 3,400 to 3,800 per year. And we also note that there is a little risk associated with implementing the calculated order quantity of 1824. Okay, so for example, if RMB implements an order quantity of 1824 cases, which is using the cost estimate based on CO equal to 32 and CH equal to 25%, and the actual cost per order turns out to be 20. If the CO turns out to be 34 and the CH turns out to be 24%, then RMB experienced only a $5 increase in the total annual cost, which is relatively very small. So from the preceding analysis, we'll say that this EOQ model is insensitive to small variations of error or all errors in the cost estimate. And this insensitivity is a property of EOQ model in general, which indicates that if we have at least a reasonable estimate of ordering cost and holding cost, we can expect to obtain a good approximations of the true minimum cost order quantity. The inventory model presented in this section is similar to the EOQ model in that we are attempting to determine how much we should order and when the order should be placed. Again, we assume a constant demand rate. However, instead of assuming that the order arrive in a shipment of size Q, which is based on the previous example. Every time we order close to 2000 units, as in the EOQ model before. Now, under the economic production lot size model, we assume that the units are supplied to the inventory at a constant rate over several days or several weeks. And the constant supply rate assumptions implies that the same number of units is supplied to inventory each period of time. It might be 10 units every day, 50 units every week, and so on. So this model is designed for production situation for which, once the order is placed, production begins and a constant number of units is added to inventory each day until the production run has been completed. And usually you see these kind of cases in manufacturing plants, where instead of receiving like one bulk of order, so you receive it slowly at a constant rate. So let's say we have a production system that produces 50 units a day, and we decide to schedule 10 days of production. And therefore we have 50 times 10 equal to 500 unit production lot size. The lot size is the number of units in an order. So in general, if we let Q becomes the production lot size, the approach to the inventory decision is similar to the EOQ model, which is we build a holding and ordering cost model that expresses the number of total cost as a function of the production lot size. And then we can attempt to find the production lot size that minimizes the total cost. One condition that should be mentioned at this time is that this model only applies to situations where the production rate is greater than the demand rate, whereby the production system must be able to satisfy the demand. For instance, if the constant demand rate is 400 units per day, the production rate must be at least 400 units per day to satisfy the demand. During the production run, the demand reduces the inventory while production adds to the inventory. Because we assume that the production rate exceeds the demand rate, each day during a production run we produce more units than demanded. So that's why, as you can see here, this is the average inventory. And this is the production phase, it goes up. And then this is the demand rate, or the demand phase, or the non-production phase. And then when it reaches the replenish point, it goes up again, and it goes up gradually, unlike the EOQ model that we have seen before. So the excess production causes a gradual inventory buildup during the production period, and when the production run is completed, the continuing demand causes the inventory to gradually decline until a production run is started. So as in the EOQ model, we are now dealing with two costs. Number one is the holding cost, and number two is the ordering cost. Here, the holding cost is identical to the EOQ model. However, the interpretations of the ordering cost is slightly different. In fact, in the production situations, the ordering cost is more correctly referred to as the production setup cost. And this cost, which includes labor, materials, the lost production costs incurred while preparing the production system for operation, is considered a fixed cost that occurs for every production run, regardless of the production lot size. Begin building the production lot size model by writing the holding cost in terms of the production lot size Q. Again, the approach is to develop an expression for average inventory and then establish the holding cost associated with the average inventory. We use a 1-year time period and an annual cost for the model. So in the EOQ model, the average inventory is 1/2 of the maximum inventory, or 1/2Q. And because in the production lot size model, a constant inventory build-up rate occurs during the production run, and a constant inventory depletion rate occurs during the non-production period. Therefore, the average inventory will be 1/2 of the maximum inventory. However, in this inventory system, the production lot size Q does not go into inventory at one point in time, and therefore the inventory never reached the level of Q units. And to show how we can compute the maximum inventory, we let D becomes the daily demand rate, and P is the daily production rate, and T is the number of days for a production run. Because we are assuming that P will be larger than D, the productions will be larger than the demand. So the daily inventory build-up rate during the production phase is P minus D. If we run production for T days, and then we place P minus D units in inventory every day, the inventory at the end of the production run will be P minus D times T. So we can see that the inventory at the end of the production run is also the maximum inventory, as you can see from the figure in the previous slide. So we can say that the maximum inventory is equal to P minus D times T, or because T is equal to Q divided by P, so by rearranging all this we get maximum inventory equal to 1 minus D divided by P times Q. Okay. The average inventory is given by 1 over 2 multiplied with 1 minus D over PQ. And the only difference between this with the EOQ model is the additions of this term 1 minus D over P. And therefore the annual holding cost is given by the average inventory times the annual holding cost per unit. And we just add, this is exactly the same as in the basic EOQ model, except with the addition in 1 minus D over P terms in this equation. So if D is the annual demand and CO is the setup cost, we call CO in this case as the setup cost, not the ordering cost. And then the annual setup cost is as follows. The annual setup cost is given by the number of production runs per year multiplied with the setup cost per run, which is D over Q times CO. And here we have, suppose that a production facility operates 250 days per year, and then we can write the daily demand D and daily production P in terms of the annual demand D and the annual production P, capital D and capital P in this case. So the daily demand, the small d, is equal to the annual demand divided by the working hours and the working days, and P, the production run daily, is given by the production run annually divided by 250. And therefore D over P for the daily is actually equal to the D over P for the annual calculation. And therefore the total cost for this economic production lot size model is given by this one, which is more or less the same as the EOQ model with some additions in terms of the 1 minus D over P equation. To determine the Q optimal, which is based on this formula, which is just rearranging all the algebra based on the previous equation, we have the Q optimal, which is given by the square root of 2DCO divided by 1 minus D over P times the holding cost. Now let's look at this another example based on the Beauty Bar soap, which is the soap is produced on a production line that has an annual capacity of 60,000 cases every year. So the annual demand is estimated at 26,000 cases, with the demand rate essentially constant throughout the year. The cleaning, preparation, and setup for the production line costs approximately $135, and the manufacturing cost per case is $4.5, and the annual holding cost is figured at 24% rate. And therefore CH is equal to I times C, which is 0.24 times $4.5, which is $1.08 per item. And what is the recommended production lot size? Using these equations, plug in all this information into the Q optimal, we have the Q optimal equal to 3,387 units. And it corresponds to the total cost of Okay, 2000. Okay, it's not being stated here, but if you compute the total annual cost using the equations in the previous slides, you get the total annual cost of 2073. Okay. The other relevant data include a 5-day lead time to schedule and a setup production run and 250 working days per year. And therefore, the lead time demand of 26,000 divided by 250 multiply with 5 equal to 520 cases, which is the reorder point. And the cycle time in this case is the time between the production runs. Using the equations for the cycle time T is given by 250 multiplied with the Q optimal divided by D. In this case, the Q optimal is 3387 and the demand is 26,000 and T is equals to 33 working days. And therefore, we should plan, in this case of beauty bar soap, we should plan a production run of 3387 units every 33 working days. Now, a shortage or a stockout occurs when the demand exceeds the amount of inventory on hand. In many situations, shortages are undesirable and should be avoided if at all possible. However, in other cases, it may be desirable from an economic point of view to plan for and allow shortages. In practice, these types of situations are most commonly found where the value of the inventory per unit is high and therefore the holding cost is high. An example of this type of situations is the New Year dealer's inventory. Often a specific car that a customer wants is not in stock. However, if the customer is willing to wait a few weeks, the dealer is usually able to order the car. So the model developed in this section takes into account a type of shortage known as a back order. In a back order situations, we assume that when a customer places an order and discovers that the supplier is out of stock, the customer waits until the new shipment arrived, and then the order is filled. Frequently, the waiting period in back order situations is relatively short, and therefore by promising the customer top priority and immediate delivery when the goods becomes available, company may be able to convince the customer to wait until the order arrived. In these cases, the back order assumptions is valid. So, back order model that we developed is an extension of the EOQ model presented before. We use the EOQ model for which all goods arrive in inventory at one time and they are subject to a constant demand rate. If we let S indicates the number of back orders or the number of shortages that have accumulated by the time a new shipment of Q is received, then the inventory system for the back order case has the following characteristics. Number one, if S back orders exist when a new shipment of size Q arrives, then these back orders are shipped to the appropriate customers, and then the remaining Q minus S units are placed in the inventory. And therefore, as you can see in this graph, the maximum Q is not at Q, but it is at Q minus S. And the second characteristic is that the inventory cycle of T is divided into two parts. T1 is when the inventory is on hand and the orders are filled as they occur. And T2 is when you can see that the Q is already a negative now. And T2 is when the stock up occur and all the new orders are placed on the back orders. So with the inventory pattern defined as such, we can proceed with the basic step of all inventory models, which is the development of the total cost model, specifically for this case in which we include the back order cost. So for the inventory model with back orders, we encounter the usual holding cost and the ordering cost. We also incur a back order cost in terms of the labor and special delivery costs directly associated with the handling of the back orders. Another portions of the back order cost accounts for the loss of goodwill because some customers will have to wait for their orders. Because the goodwill cost depends on how long a customer has to wait, it is customary to adopt the convention of expressing back order costs in terms of the cost of having a 1 unit on back order for a stated period of time. And this method of costing back orders on a time basis is similar to the method used to compute the inventory holding cost, and we can use it to compute a total annual cost of back orders once the average back order level and the average back order cost per unit per period are known. Now in this model, the maximum inventory is at Q minus S instead of Q. And in terms of the time, we have T equal to T1 plus T2. And we only have the inventory carried at T1. And therefore, the average inventory of QS minus the average inventory in the EOQ is Q divided by 2, right? So the average inventory in this case is Q minus S divided by 2, but this can only be computed on T1. And therefore you can see that the average inventory in this case is 1 over 2 times Q minus S times T1. And for the T2, we multiply with 0 because there's no, there's no inventory at T2. And we divide with T, where T is equal to T1 plus T2. So D is the daily demand, okay? And we know that the maximum inventory that will be used up in this case is equal to T1 equal to Q minus S divided by D. And the length of the cycle must be T equal to Q divided by D. And therefore from here we can compute the average inventory as Q minus S squared divided by 2 times Q. And the formula for the annual number of orders is D divided by Q. And using the same logic, we can apply this to the average inventory for the average back orders, which is given by the orders is only happen at T2. Yeah. So for T1, we multiply with 0, and at T2, it's given by S divided by 2, and B divided by T. So because we know that the maximum number of back orders will be used up in T2, which is equal to S divided by D days, so the length of the cycle is still at T equal to Q divided by D. And then we can compute the average back orders, such as S squared divided by 2Q. And given all this, now we can compute the total cost. So the total cost, it has 3 parts. So we have the first part, which is the holding cost, and second part is the ordering cost, and the third part is including the back order cost. The Q optimal is given by the square root of 2 times D times the ordering cost divided by the holding cost, multiply with this term where we have the sum of holding cost and the back order cost divided by the back order cost. And to get the optimal planned back orders as optimal, so as optimal is given by the Q optimal times with this term where we have the holding cost divided by the holding cost plus the back order cost. And therefore, the reorder point is given by dm minus the S optimal. Now let's look at another example. This is an example on the inventory model with planned shortages. We have the Higley radio components. They have a product for which the assumptions of inventory with back orders are valid. So these are some information that we have from this company. They have a demand, the annual demand of 2,000 units. A manufacturing cost of unit is $50. Annual holding cost 20% per rate, 20% rate, and $25 cost per order, and they have a lead time of 5 days. So here we have M equal to 5, CO 25, the CH, it is 20% times $50, so CH is equal to $10 per unit per year, and we have a demand of 2,000 units per year. So the company is considering the possibility of allowing some back orders to occur for the product. So the annual back order cost is estimated to be $30 per unit per year. So using all this information, the Q optimal is given by, just plug in all this information where the CB is equal to 30, and we have the Q optimal of 150, and S is given by 115 times this term, and we get 29. Yeah. So if this solution is implemented, the system will operate with the following properties. So number one, the maximum inventory is Q minus S, which is 115 minus 29 equal to 86 units. And the cycle time is given by T, which is Q divided by D times 250. So we have 115 divided by 2000 times 250, which is 14 working days. And the reorder point, which is DM minus S, D is 2000 divided by M is 250, and then we have minus with 21, we get 11. So the total cost for the holding cost is 332, and the ordering cost is 435, and the back order cost is 110, and adding this all together, we have a total cost of $867. Okay, now we consider another variations of EOQ model, which is still in the deterministic model. Okay, the quantity discount. The quantity discounts occur in numerous situations for which the supplier provides an incentive for large order quantity by offering a lower purchase cost when items are ordered in larger quantities. In this subtopic, we show how the EOQ model can be used when quantity discounts are available. Okay, because it may happen that the calculated Q or the Q optimal may be too small to qualify for the assumed discount price. Therefore, the following 3 steps must be followed. The first step is, for each discount category, we compute the Q optimal using the EOQ formula based on the unit cost associated with the discount category. So number 2 is, for the Q optimal that is too small to qualify for the assumed discount price, we adjust the order quantity upward to the nearest order quantity that qualifies for the discount. And for step 3, for each order quantity resulting from step 1 and step 2, we compute the total annual cost using the unit price from the appropriate discount category. The order quantity yield the minimum total annual cost is the optimal order quantity. So basically, what does it mean here for this step 1 to step 3? So first is we compute the basic EOQ model first, and we look at the price. If the price falls into the quantity which doesn't enjoy any discount, then we try to increase the number of quantity. If, let's say, using the basic EOQ model, and then you compute that the amount is 700, well, you can only get the discount if you buy 1,000. So let's say if you buy 1,000, then the discount is 20%. But if you buy 700, there's no discount. And then first is you do not look at the discount at all. First is you just compute the Q optimal using the basic EOQ model. And then the basic EOQ model tells you to have your inventory at Q equal to 700. But 700, you do not enjoy any discount. And then you would consider that, what if I just increase by 300? What if I buy 1,000? Would that result in a significant decrease in the total cost? And then it happened to be that, when you buy 1,000, and the total cost decreases compared to when you buy the 700. So that is when all these steps occur. So first is step 1, you start with the basic EOQ model, and step 2 is maybe you just increase it to, to enjoy the discount, and then you see, yeah, and then we reiterate again until we get the quantity that will minimize the total cost. Now let's look at this example. Okay, we have a 3 discount category. So if you buy from 0 to 999 units, there's no discount, and the unit cost is $5. Okay, and let's look at the second one. The second one shows that the minimum order size is 1,000, and if you buy at least 1,000, you get a discount of 3%, and the cost per unit is 4.85. And if you order more than 2,500, then you will enjoy a 5% discount, and the price reduced to 4.75. Okay, so in this case, first is use the basic EOQ model, and the basic EOQ model tells you that the Q optimal is 700. All right, the Q optimal is 700 without taking into account any of the possible discount that you might enjoy. So you think that, okay, now with my based on my ordering cost and based on my holding costs, I think that the quantity that would minimize my total cost is 700. But it could be that you think that, hey, what if what if I want to enjoy this discount? So what you do is, okay, you try to use this unit cost. Okay, in this case, let's say you consider the 3 different prices: $5, 4.85, and 4.75. For all the 3, you compute the Q optimal using the basic EOQ model. And for the first one, with the unit cost of $5, you get 700. Even with the cost of 4.85, it tells you that the optimal ordering quantity or the optimal inventory is 711. And even at 4.75, it tells you that the Q that will minimize the total cost is 718. But for all these figures, actually none of this you will enjoy the discount. So you think that, okay, what if, I know that the model suggests me to have like 700, 711 or 718, but what if I just try to adjust the quantity so that I can enjoy the discount? Okay, so what you do is you adjust the quantity. So for the first category, because it doesn't matter whether you buy 0 or 999, there's no discount. So but you have computed that if you want to minimize the total cost, then you have to choose this Q optimal, which is 700. So the total cost is 25,700. So in order for you to enjoy the 3% discount, you need to order at least 1,000. So you say, okay, maybe I can order 1,000, which is the minimum of this category. And with 1,000, you compute the total cost, which is 24,000. Okay, 24,000. But in the third category, okay, if let's say you want to buy 2,500 units, okay, and you enjoy the 5% discount, and then you compute the total cost. The total cost equal to 25,000. So comparing all this, actually the one that minimizes the total cost is this 1,000 units, where the total cost is much less than if you just buy the 700 units. So of course, in this decision, in this case, you would choose to buy the 1,000 instead of 700. Now let us go to the second part of the lecture, which is based on the probabilistic demand. So the inventory model we discussed before, or we discussed earlier, were based on the assumption that the demand rate is constant and deterministic throughout the year. So you know exactly that it's going to be around 2000. Okay, so we developed minimum cost order quantity and reorder point policy based on these assumptions. However, in situations for which the demand rate is not deterministic, other models treat demand as probabilistic and best described by a probability distribution, which is more practical. In these sections, we consider a single period inventory model with probabilistic demand. So the single period inventory model refers to the inventory situations for which one order is placed for the product. At the end of the period, the product is either sold out or there is a surplus of unsold item that will be sold for a salvage value. So the single period inventory model is applicable in situations involving seasonal or perishable items that cannot be carried in inventory and sold in the future periods. So seasonal clothing items such as bathing suits and winter coats are typically handled in a single period manner. And in these situations, a buyer places one pre-season order for each item and then experience a stock out or hold a clearance sale on the surplus stock at the end of the season. No items are carried in inventory and sold the following year. The newspaper are another example of a product that is ordered one time and it is either sold or not sold during the single period. And although newspapers are ordered daily, they cannot be carried in inventory and sold in later periods, and therefore newspapers order may be treated as a sequence of single period model, which is each day is one period and one period is separate from one another, and a single period inventory decision must be made every day for newspaper. Because we order only once for the period, the only inventory decision we must make is how much of the product to order at the start of the period. So obviously, if the demand were known for a single period inventory situation, the solution would be easy. We would simply order the amount we knew would be demanded. However, in most single period models, the exact demand is not known. In fact, forecasts may show that demand can have a wide variety of values. So if we are going to analyze this type of inventory problem in quantitative manner, we need information about the probabilities associated with various demand values. And therefore, the single period model is presented in this lecture based on the probabilistic demand. Now let us consider a single period inventory model that could be used to make a decision on how much to order. And for this one, we use the Neiman Marcus, which is a chain of department store probably in New York City. So they are selling shoes, and the shoe will be part of the company's spring-summer promotion, and it will be sold through 9 retail stores in the Chicago area. Because the shoe is designed for spring and summer month, it cannot be expected to sell in the fall. So Neiman Marcus plans to hold a special August clearance sale in an attempt to sell all shoes which is not sold by July 31st. So the shoes cost $700 a pair and a retail of $900 a pair, and the sale price is $600 a pair, and all surplus shoe can be expected to sell during the August sale. So if you were the buyer for the Neiman Marcus, how many pairs of the shoe would you order? So to answer the question of how much to order, we need information on the demand for the shoe. Specifically, we would need to construct a probability distribution for the possible value of demand. And let us suppose that the uniform probability distribution is for this example. So in particular, note that the range of the demand is between 350 to 650 pairs of shoes, with an average or the expected demand of 500 shoes, which is in the middle here. and this is a uniform distribution, so there's no anticipations for any seasonality in this case. So the incremental analysis can be used to determine the optimal order quantity for a single period inventory model. Incremental analysis addresses the how much to order question by comparing the cost or loss of ordering one additional unit with the cost or loss of not ordering one additional unit. So the cost involved is given by below. Okay, so the CO is the cost per unit of overestimating demand. So remember that the CO is not the same as the CO that we have discussed before. So the CO is the cost of overestimating the demand, and this cost represents the loss of ordering one additional unit and find that it cannot be sold. And the CU is the cost of underestimating the demand, which is the cost of opportunity loss of not ordering one additional unit and find that it could have been sold. So in the Neiman-Marcus problem, the company will incur the cost of overestimating the demand whenever it orders too many pairs and has to sell the extra shoes during the August clearance sales. So the cost of overestimating the demand is equal to the purchase cost, which is $700, minus the August sales price, which is $600, and therefore the cost of overestimating, or the CO, is equal to 100. And the cost of underestimating the demand is the lost profit, or we call this as an opportunity lost, because a pair of shoes that could have been sold was not available in inventory. The per unit cost of underestimating the demand is the difference between the regular selling price per unit, which is $900, and the purchase cost per unit, which is $700. And 900 minus 700 is $200. So actually we do not know what is the exact level of demand for this shoe, and therefore we have to consider the probability of the demand and therefore the probability of obtaining the associated costs or losses. So if you look at the previous graph, we can see that the average of the expected demand is 500, because 500 is the middle point. Okay, so now let us look at this optimal ordering quantity, which is the Q optimal, and such that the expected loss due to underestimating the demand is equal to the expected loss due to overestimating the demand when ordering one additional unit. So what is the expected losses of CO and CU? Okay, understating and overstating the demand, it is given by the EL of Q multiplied with the cost of underestimating the demand when the demand is actually higher than the Q optimal. And the EL Q plus 1 is given by the cost of overestimating when the demand is actually less than Q. Okay, because understating and overstating demand are complementary events, so we can write the probability of the demand higher than a certain value is actually equal to 1 minus the probability of the demand less than a certain Q. And therefore we can rewrite the expected loss, which is equal to the cost of underestimating the demand multiplied with 1 minus the probability of when the demand is actually less than a certain Q. And we plug the ELQ and ELQ plus 1 equality, and we solve for the demand of less than Q, and it gives us the probability of the demand less than a certain value of Q is given by the CU divided by CU plus CO. Okay. And in the Neiman-Marcus problems, we can see that CO is equal to 100 as we calculated earlier, and the CU is equal to 200. For the optimal order size for the shoe must satisfy the following condition, which is the property of demand less than the certain number of Q is equal to CU divided by CU plus CO equal to 2/3. So we find the optimal order quantity Q by referring to the uniform probability distribution that describes the designer shoe demand and finding the value of Q that provides this probability, where property of the demand less than a certain value must be equal to 2.3 or 2/3. So to find these solutions, we note that in the uniform distributions, the probability is evenly distributed over the entire range of minimum 350 to the maximum of 650, and therefore we can satisfy the expression of Q by moving 2/3 of the way, okay, from 350 to 650. And this range is, you get 650 minus 350, so the range is 300. So we move 200 units from 350 to 650. So this is the 2/3 of the range of the possible sales. And in doing so, it provides the order or the optimal order quantity of 550 pairs of shoes. Example of a single period inventory model with probabilistic demand. We consider the situation faced by this nationwide car rental. This company must decide how many automobiles to have available at each car rental location at specific points in the time throughout the year. So using the several locations at Myrtle Beach, South Carolina location as an example, management would like to know the number of full-size automobiles to have available for the Labor Day weekend. Based on the previous experience, the customer demand for full-size automobiles for the Labor Day weekend has a normal distributions with a mean of 150 automobiles and the standard deviations of 14 automobiles. So in the previous example, we were considering a uniform distributions, and this time around is a normal distribution, so there are some variations in the demand. So these nationwide car rental situations can benefit from the use of a single period inventory model. The company must establish the number of full-size automobiles to have available prior to the weekends. The customer demand over the weekends can then result in either a stockout or a surplus. Let us denote the number of full-size automobile available by Q. And if Q is greater than the demand, then Nationwide will have a surplus of the car. And the cost of a surplus is the cost of overestimating the demand. And this cost is assumed to be at $80 per car, which reflects in part the opportunity cost of not having the car available for the rent elsewhere. So if Q is less than the customer demand, then Nationwide will rent all available cars and experience a stockout or a shortage. And the shortage results in an underestimation cost of $200 per car. And this figure on the right hand side, or this figure reflects the cost due to the lost profit and the lost goodwill of not having a car available for a customer. And given this information, we want to ask the question of how many full-size automobiles should Nationwide make available for the labor weekend. And here we have the cost of underestimations, which is $200, and the cost of overestimations, which is $80. And the optimal order quantity must satisfy the following condition, which is the property of demand, which is less than a certain Q, is given by CU divided by CU plus CO. And we just plug in all this CU and CO into the equations, and we have the probability of 0.7143. So the figure of probability of 7143, if we look at this graph, it is just over the mean of 150, and depending on the Z value, the Z value of 5.7 okay, indicates okay, the quantity of the Q can be computed as mu plus the Z value times the standard deviations, which is 150 plus 0.57 times 14, which is equal to 158 automobiles. Go to the next subtopic on the order quantity and the reorder point model with probabilistic demand. So just now we consider a single period inventory model with probabilistic demand, and here we extend our discussions to a multi-period order quantity reorder point inventory model with probabilistic demand. So in the multi-period model, as you can see on the right hand side, the graph shows that it's not just one-time demand, but it's like multi-period demand, and each of the periods have like a different maximum Q for each of the periods, and even the time is also varies. So whenever the inventory position reach the reorder point, around somewhere here, okay, and therefore the order for the Q unit is placed. But because the demand is probabilistic, the time to reorder point will reach the time between orders, and the time of the order of Q units will arrive in inventory cannot be determined in advance. So the inventory pattern for the order quantity, the reorder point model with probabilistic demand, will have the general appearance as in this picture. And note that the increases or jumps in the inventory occur whenever an order of the Q units arrived in the inventory, and here we assume that the inventory arrived at one point of time. So the inventory decrease at a non-constant rate based on the probabilistic demand, and the new order is placed whenever the reorder point is reached. At times, the order quantity of Q units will arrive before the inventory reaches zero. And however, at other times, higher demand will cause a stock up before a new order is received, such as you can see somewhere here. Okay. As with other order quantities, the reorder point models, the manager must determine the order quantity Q and the reorder points R for the inventory system. So actually, what we're going to discuss here is the simplified versions of this model, because to get the exact mathematical formulations of this order quantity and the reorder point for this particular model, it is beyond the scope of our lecture. Okay, but we can present a procedure that can be used to obtain a good and workable order quantity and reorder point inventory policy. So now let us take this example. We have Dubco lighting distributors. So Dubco purchases a special high intensity LED light bulb for industrial lighting system from a well-known light bulb manufacturer. Dubco would like a recommendation on how much to order and when to order so that a low-cost inventory policy can be maintained. The pertinent facts are that the ordering cost is $12 per order, and one bulb costs $6, and Dubco uses 20% of annual holding cost rate for its inventory. And therefore, the holding cost is given by I times C, which is 0.2 times $6, which is equal to $1.2. This company has more than 1,000 customers and experiences a probabilistic demand, and in fact, the number of units demanded varies considerably from day to day and from week to week. So the lead time for a new order of light bulbs is 1 week, and historical sales data indicate that the demand during a 1 week lead time can be described by a normal probability distribution with a mean of 154 and a standard deviations of 25. So the normal distributions of demand during the lead time is shown in this graph. And because the mean demand during 1 week is 154 units, we can anticipate a mean or expected annual demand of 154 times 52 weeks, which is equal to 8,008 units per year. So now we go to the questions. The first question is how much to order. So although we are in a probabilistic demand situations, we have an estimate of the expected annual demand of 808 units. And therefore we can apply the EOQ model, the basic EOQ model, as an approximation of the best order quantity with the expected annual demand used for T. And in this case, the Q optimal is given by this formula. So you just multiply using D equal to 0.8008, and we have the optimal quantity of 400 units. So if we do the sensitivity of the EOQ model, we learned that the total cost of operating an inventory system was relatively insensitive to order quantities that were in the somewhere near Q optimal. And using this knowledge, we expect 400 units per order to be a good approximation of the optimal order quantity, even if the annual demand were as low as 7,000 units, or it might be as high as 9,000 units. An order quantity of 400 units should be a relatively good low-cost order size. And therefore, given our best estimates of the annual demand at 8,000 units, we will still use Q optimal of 400. So we have established the 400 units order quantity, and we ignore the fact that the demand is probabilistic. And assuming this Q equal to 400, the company can anticipate placing an approximately 20 orders per year. So 20 is obtained by taking 8,000 divided by 400, which is equal to 20. So there will be 20 cycles with an average of approximately, if we consider the working days is 250, so 250 divided by 20 equals to 12.5 working days between the order. And then next we answer the questions on when to order. So now we have a mean lead demand of 154 units. And you might first suggest 154 unit reorder point. However, we need to consider the probability of demand. And now these probabilistic assumptions become important. So if the mean lead time demand is 154 and the demand is symmetrically distributed around this mean value, and the lead time demand will be more than 154 units, which is roughly 50% of the time. So when the demand during the 1 week lead time exceeds 154 units, the company will experience a shortage. And therefore, using the reorder point of 154, which is true for 50% of the time, and assuming this, it means that there's a 10 out of 20 orders per year on average will result in the shortage of bulbs before the new supply arrived. And this shortage would most likely be viewed as unacceptable. So by looking at this lead time demand distribution on the right hand side, so the mean is somewhere here, 154. So this is like 95%. The demand is less than a certain value of R, and we allow certain demand to be more than R. This 5% and 95% is depending on the domain knowledge. But I think 5% would be acceptable if, let's say, only 5% of the time you'll have some shortages that will reduce your the cost, yeah, especially the opportunity cost. So given this distribution, now we can determine how the reorder point, or the R, would affect the probability of a stockout. We can find the probability of a stockout by using the lead time demand distribution to compute the probability that the demand will exceed certain value of R. So now we could now approach this issue by defining a cost per stock out, and then we attempt to include this cost in a total cost equation. Or we can ask the management to specify the average number of stock out that can be tolerated per year. If demand for a product is probabilistic, a manager who will never tolerate a stock out is being somewhat unrealistic, because attempting to avoid stock out completely will require high reorder point, and therefore it will result in high inventory and an associated high holding cost. So suppose in this case the management is willing to tolerate an average of 1 stock out per year, and because we place 20 orders per year, and this decision implies that management is willing to allow demand during the lead time to exceed the reorder point one time, or 1 out of 20, or equal to 5% of the time. So the reorder point R can be found by using the lead time demand distribution to find the value of R with a 5% chance of having a lead time demand that will exceed this figure. So from the standard normal probability distribution table, we can see that if we take 1 minus 0.05, so we have 0.95, and this is the area on the left tail of the normal probability distribution, and this corresponds to Z value of 1.645. And therefore, for the assumed normal distribution, and for the lead time demand with mu equal to 154 and the standard deviation of 25, the reorder point R is equal to the mean, which is 154 plus Z 1.6 times 25 equal to 195 units. So in general, R is equal to the mu plus Z times sigma. So the recommended inventory decision is to order 400 units whenever the inventory reach the reorder points of 195, because the mean or the expected demand during the lead time is 154, so the difference is 195 minus 154 is equal to 41 units, and this unit serves as the safety stock, which may absorb higher than usual demand during the lead time. So basically with this 41 units, we can say that 95% of the time, or 195 units, will be able to satisfy the demand during the lead time. Okay. Yes. The order quantity, the reorder point inventory models, which we discussed earlier, requires a continuous review of the inventory system. So in the continuous review of inventory system, the inventory position is monitored continuously so that an order can be placed whenever the reorder point is reached. The computerized inventory system can easily provide the continuous review required by the order quantity and the reorder point model, so you don't have to compute it manually. An alternative to the continuous review system is the periodic review inventory system. So with a periodic review system, the inventory is checked and reordering is done only at specified points in time. So maybe every week or every month you will compute the inventory. So an example of this is inventory may be checked and orders placed on a weekly or monthly basis. Business handle multiple products. The periodic review system offers the advantage of requiring that orders for several items be placed at the same preset periodic review time. With this type of inventory system, the shipping and receiving of orders for multiple products are easily coordinated. Based on the previous models we discussed here on the order quantity reorder point system, the reorder points for various products can be encountered at substantial different points in time, therefore making the coordination of orders for multiple products more difficult. Now, we assume that the lead time is less than the length of the review period, and an order is placed at the review period will receive prior to the next review period. And in this case, the how much to order decision at any review period is determined using the following equation: Q given by M minus H. So M is the replenishment level and H is the inventory on hand at the review period. And because the demand is probabilistic, the inventory on hand at the review period H will vary, and therefore the order quantity that must be sufficient to bring the inventory position back to its maximum or replenishment level M can be expected to vary each period. So here what is constant is the period, and what will vary is the quantity. So for example, if the replenishment level for a particular product is 50 units and the inventory on hand at the review period is 12 units, so here H is equal to 12, and therefore the order is Q given by M minus H, where M is 50, H is 12, so Q is 38 units. So under the periodic review model, enough units are ordered each review period to bring the inventory position back up to the replenishment level. So the graph on the right hand side shows a typical inventory pattern for a periodic review system with probabilistic demand. And if you look at the graph, you can see that the time between the periodic review is predetermined and fixed. So the range for the time is always the same. But the order quantity Q at each review period can vary, and it's shown to be different between replenishment levels and the inventory on hand. Finally, as with other probabilistic models, an unusually high demand can result in an occasional stock out. So the decision variable in the periodic review model is the replenishment level M. So to determine M, we could begin by developing a total cost model, including the holding, ordering, and stock up cost. Instead, we describe an approach that is often used in practice. And in this approach, the objective is to determine a replenishment level that will meet a desired performance level, such as reasonably low probability of stock up or a reasonably low number of stock up per year. Now let's look at this example. And in this example, we have dollar discount company, and we assume that management's objective is to determine the replenishment level with only a 1% chance of a stock out. So in the periodic review model, the order quantity at each review period must be sufficient to cover demand for the review period plus the demand for the following lead time. Suppose that an order is to be placed at time t. To determine this order quantity, we must know that the quantity ordered at time t must last until the next time inventory is replenished, which will be the time t plus the review period plus the lead time. And therefore, the total length of the time that the order quantity at time t must last is equal to the review period plus the lead time. And the figure on the right hand side shows the normal probability distributions of demand during the review period plus the lead time period for one of the products. And the mean demand for this particular product is 250 units. The standard deviation is 45. And given these situations, logically we would use to establish M, which is similar to the logic we used to establish the reorder point in the previous example. So here you can see that if we have a replenishment level M with a 1% chance that the demand will exceed the replenishment level, is given by somewhere here. Okay, and to get this figure, so M is equal to the mu, which is 250, plus the Z value of 1%, or correspond to 0.99 here, corresponds to 2.33 multiplied with sigma of 45, and here we have M is equal to 355 units. So if the demand had been deterministic rather than probabilistic, the replenishment level would have been the demand during the review period plus the demand during the lead time period. And in this case, the replenishment level would have been 250 units, and we would assume no stock out would occur. However, with the probabilistic demand, we have seen that higher inventory is necessary to allow for uncertain demand and to control the probability of a stock out. And in this problem, how much of the safety stock necessary to absorb any higher than usual demand during the review period? So we have 355 minus 250 units, which is M. This is equal to 105. So 105 would be the safety stock that would be necessary in order to absorb any spike in the demand during the review period, plus the demand during the lead time period. And this safety stock limits the probability of a stock out to 1%. And that is all for the inventory management. I mean, just like the queuing system. So you just, there will be a set of different equations for different inventory model. So first is you need to really understand what is the model that the problem have, and then based on the problems, then you determine what will be the best model that you can use. So I think that's all for this lecture. Thank you very much.